Alright, here we are. We're in chapter 2 talking about Newton's first law of motion. Newton's three laws of motion were going to be the next three chapters, and we're going to start with the first one today. So first, let's do a little background about what people thought about motion before Newton came along. The first people to say much about motion was Aristotle, back in about 300 BC, 300 years before Christ. And so it's pretty far back there. People running around in bed sheets and things like that. And he thought that basically there were two types of motion. There was natural motion and unnatural motion. So, for example, rocks fell down because they were of the earth. They were part of the earth, and therefore it made sense that they would go down. All right? On the other hand, smoke was like air or gas, and so it would rise toward the air. And so those were just natural motions. Natural motions were things that occurred because they were part of nature, and that's just the way they happened. And they happened without us having to do anything to them. Therefore, they were natural. The moon would move around the sun, move around the earth, and the earth and the sun and the earth, they probably thought that the earth went around the sun, but the sun went around the earth. But at any rate, all those kind of motions with planets and so forth were caused by natural motions, okay? An unnatural motion then was anything that you had to make happen. If I wanted to lift a rock up, for example, that was an unnatural motion, so that's why I had to apply a force to it in order to pick it up. Had it been a natural motion, it would have lifted itself up, but that's just not natural for rocks to go up, and so it didn't do that. Okay, it wasn't a bad idea, it just wasn't correct. Okay, and that went along. That was before, like I said, before Christ by 300 years, and that went on for quite some time. It wasn't until Galileo, thousands of years later, that said that's probably not right. He started studying motion, and he made some advances. He started looking at balls running up and down ramps, and basically he noticed that if they were on downward facing ramps, then of course the speed would increase, and the steeper the ramp, then the more the speed would increase. All right. On the other hand, if they're going uphill, the speed would decrease. The steeper it is, the quicker they would decrease. All right. And so basically he came up with the idea of gravity. I don't know if he actually called it gravity, but the idea that there was something that pulled things down, a force acting on it down, and therefore if it was slanted down, it would go faster, and the steeper the slope, until finally the very steepest slope would be if you just dropped objects off the building. Of course, he's famous for dropping objects off the Leaning Tower of Pisa. Whether he actually did the Leaning Tower of Pisa or not, but he did do some experiments with falling objects. Now, but he noticed if there's on no slope and you roll an object, well, then since there is no upward slope or downward slope, it should continue at the same speed. Okay? But in fact, it did not. If you roll objects on straight objects, they would, a flat surface, they would eventually come to a stop. And so he came up with the idea of friction to explain that friction was where the object rolling across the floor, the ball, whatever, would rub against the floor, and because of that, it would cause it to slow down. And he actually came up with the term inertia, which we will think of in Newton's first law here in a little bit, which means basically that an object resists any change in its motion. If it's moving, it wants to keep moving. If it's stopped, it wants to stay stopped. Okay? And so he came up with that idea of inertia to begin with. And basically he said the inertia was a measure of its mass. And that's an important point. Inertia is not equal to mass, but inertia depends directly and only on an object's mass. Someone said, well, which has more inertia? If I have a Volkswagen Bug that's going 60 miles an hour, or a semi-truck that is stopped and not moving at all. Well, we know which one we'd rather step in front of. We'd rather step in front of the semi-truck because it's not going anywhere, so it won't hurt us. Whereas even the Volkswagen Bug is going to hurt if it's going 60 miles an hour and possibly kill us. All right, but as far as inertia goes, they have the same amount of inertia, because inertia just means how hard is it to change their motion. It's still harder. It takes more force to make that semi-truck start moving than it would to stop the moving Volkswagen Bug. Okay, and so what we usually are thinking really has to do more with momentum, which has to do with the mass times the velocity, or how fast they're going, and we'll get to that later in chapter 5. But inertia really just depends on the mass. Think of it this way: if you had the Volkswagen Bug stop on the side of the road and you want to try to push it to get it going, or you had the semi-truck, which one would be the hardest to get moving, or to change its motion from zero into actually starting to roll down the road? Well, obviously it would be the semi-truck. Or think of them both going the same speed. You have a Volkswagen Bug or a semi-truck. Obviously we don't want to step in front of either one, but obviously it would take more energy to stop the semi-truck, and so therefore it has more inertia, and it would be harder to change its speed than it would be for the smaller Volkswagen. Alright, and so those are some ideas that Galileo came in. Now he also did some other things with speed that we're going to talk about before we get to actually Newton's first law of motion. Okay, speed is basically defined as distance covered per unit time, and Galileo was the first person to do a lot of experiments in the scientific method as we know it today, and to try things out and to test them like that. And he basically, the hardest part, of course, was to time things, because he didn't have sophisticated watches and stuff, stopwatches and so forth that we have today. And so he would have to use, for example, perhaps his pulse, because that would be a fairly constant rate, and he could use that to measure things. But obviously the difference between 6 heartbeats and 7 heartbeats would be kind of iffy. 6.5 heartbeats, it wasn't very exact, but it was good enough for him to make some general rules. And so the formula for that is speed is equal to distance divided by time. Alright, so speed is equal to distance divided by time. And that formula is basically what we do. Now, in this course is called Conceptual Physical Science, or at least the book that we're going to be using. And the idea is that we're studying the ideas. How does it work? Now, are we going to have math? Yes, we're going to involve math, but we're not so much concerned about the calculating the formulas as much as understanding what the formulas mean. Okay, if we know that, that's what we're really looking for. So if we look at the speed formula, speed is equal to distance divided by time. What this means is, if we can go a bigger distance, this number gets larger in the same amount of time, then what happens to our speed? Well, if the top number gets larger, that's going to make this fraction a bigger number, and therefore we have a faster speed. Alright, if we go a less distance in the same amount of time, then that means we have a lower speed. Alright, also it could be, say we both run 100 meters. Usain Bolt and I can both run 100 meters. Same distance. But he can do it with less time. So if the bottom number is smaller, time in the denominator, if that number is smaller, then the speed is going to be faster. And so he's much faster than I am. Even though I run the same distance, it takes me a larger time. Since I'm dividing by a larger number, that's going to make the speed smaller. Okay? And so that's basically all this formula is saying. Speed is directly proportional to distance. If we cover more distance in the same amount of time, then we're going to have a higher speed. But it is inversely proportional, or the opposite, of time. If it takes me more time to run the distance, then I'm going to have a slower speed. All right, so they're inversely proportional to each other. Okay. Now, there are different kinds of time that we can be talking about. All right. For example, if I go on a trip, and say I go from Fort Worth and I travel all the way up to Amarillo, okay, and I find out that for that trip, my speed, I said, so what was your speed for the trip? And I said, well, it took me, let's say, 7 hours, and I went X number of miles, and so I take that distance, the total distance that I traveled, divide it by the total time it took me, and I say my speed was 60 miles per hour. All right, but was I actually going 60 miles per hour the whole trip? Well, hopefully not, because going through towns, a lot of times the speed limit was probably below that. Okay, I know sometimes on the highway the speed limit was higher than that, and I was probably going faster than that. So the question is, well, what's the difference? Well, what I'm really talking about on a trip or extended thing like that is the average time. And average speed, excuse me. An average speed is where you take the total distance you traveled divided by the total time it took you to go that distance, and that gives you the average. At some point, I was stopped at red lights, okay, and my speed was 0. At some times, I may have slipped, just because I was sleepy, I'm sure, and gone over the speed limit and gone 75 or 80, okay? But on the average, my speed was 60 miles per hour. Now, if I include rest breaks, then I was going 0 miles an hour for, say, 10 or 15 minutes, then that's going to decrease my average speed, all right? And so that would be average speed. And a lot of times that's really what we're talking about. We're talking about what is your average speed. If I wanted to know how fast someone's running the 100-yard dash, I would really just be looking at an average speed. How long did it take them to run the whole distance? And that would be their average speed. I could calculate their average speed for that race. All right. On the other hand, if I were on my trip and I look in the rearview mirror and I see flashing lights and I know we have a problem here, is it going to do any good if I tell the highway patrolman that, well, my average speed was just 60? Not really. Because he doesn't really care what my average speed was. He cares about how fast I was going at the moment I went past his radar gun. All right? And that is known as the instantaneous speed. How fast you're going at any given minute. All right? Moment. If you have a radar gun, you could calculate someone's instantaneous speed all along the race and see how fast they're going. You could do your car, your speedometer in your car is giving your instantaneous speed. Actually, there's probably a little bit of delay of about a half a second or so, but that's pretty close to your instantaneous speed. How fast are you going right at that moment? All right, and yet usually it's constantly changing. All right, that would be instantaneous speed. Now, things not to tell the police officer once you get corrupt would probably this would be a good example. Can we speed this up? I'm in a hurry. Well, obviously that's why you're on the side of the road in the first place, but probably not a good thing to say. All right, and the last type of speed we're going to talk about is going at a constant speed. A constant speed is a speed that does not change at all. In other words, if I'm going at 60 mile per hour constant speed, I'm going 60 miles an hour. Period. It doesn't speed up, doesn't slow down, it stays at exactly. Now, to be honest, it's very, very rare in the real world that anything moves at exactly a constant speed of whatever. If you put cruise control in your car, that becomes a lot closer to constant speed. But even that is not, you can feel it speeding up or slowing down slightly, especially if you're in the mountains when they're hills, it may have to speed up and slow down a lot. To try to keep it at that same speed. So a constant speed does not happen very often in the real world as we know it. All right. The last thing we want to cover real quickly is the difference between speed and velocity. A lot of times in the book and in physics books, you will hear them use them as if they were the same thing. And yet they'll all make a point at one point that they're not. The difference is this. Speed is how fast you're going. If I'm going 60 miles per hour, that is my speed. If I have the speed plus a direction, then that is my velocity. If I'm going 60 miles per hour north, then that is an example of a velocity, or northeast, or west, or to the right, or to the left. But as long as there's some type of direction to it, that is velocity. And because it has a magnitude, or how fast I'm going, that's the magnitude, and it tells me in what direction I'm going, that is considered what we call a vector. So we say velocity is a vector quantity. All right, and now the other thing we need to know about that is if we go at a constant speed, that means our speed does not change. But if we're going to a constant velocity, then that's a little bit different. That means that our speed is not changing. We're not speeding up. We're not slowing down. But we are also not changing direction, because if we change direction, then we change our velocity. And to be a constant velocity, the velocity cannot change. So a constant velocity means we're going the same speed in the same direction. The same magnitude, the same speed, and the same direction. All right. In our next one, we'll talk about relative motion. But before we do that, if you have a race car running around the racetrack at TMS, is it possible to go at a constant speed? And B, is it possible to go at a constant velocity? The answer will be in our next lecture video.